Get started. This should be a slightly shorter lecture than usual. So there's still a Canvas activity out. There's a homework is due a little later this week. I've added some additional hints to make it a little easier to get data out of the homework for those of you that are using especially the older version. You can use the newer version that you built in Lab 7, and that gives you a little more facilities that Arena has. But the older version, I've added to the second page of this homework some notes about, there's a .out file that we usually don't talk about, but I've mentioned it, that it's like a text file that actually has all of the info that would normally be in Crystal reports. It's just not in like a comma separated values format. I've also sort of added notes about how you use the output analyzer with the old elements, if that wasn't clear. And so hopefully that's in there, but also if you use the process analyzer, I made a note that if you, in the box and whiskers charts, you can actually click on the chart, say chart options, and it'll show you all the confidence intervals that it is plotted. So in principle, you can actually have the process analyzer run all of your replicates all at once and get all of your confidence intervals ready for there to report, and even have a nice graphical plot that shows you everything all in one. So getting used to using the process analyzer and making these Arena simulation experiments a lot easier. So there's no new labs coming up here. The next two lab periods, this week and next week, are just open labs, and then after that, that'll be our presentation day. So your last lab period for the semester is the period where you'll present your final project. The final project, just things to keep in mind. There is a note in the final project's document about a submodel requirement. This is just our heuristic to make sure you're building something that's sufficiently complex, and so the submodel is something that was introduced in a previous lab where you can basically highlight a bunch of elements and then tell them to form a submodel that ends up being it doesn't actually change the model, it just changes the top level visualization, so it hides them all behind an element. Then if you drill down into that element, you can see them all again. And so normally you wouldn't hide like one element behind a submodel, you'd hide several. And so we're looking for sort of an objective measure of, is it more complicated than just a simulation of an MM1Q, then maybe it has enough components that you'd hide behind kind of a submodel. But the spirit of that is really more of, are you asking a question that really warrants simulation study? So if you're just saying, does the service, or does the response time of the system go down if I add another server? Well, we probably know that ahead of time, so we don't need a simulation for that. Now, if you're asking something a little more complex, like if I trade in servers that are cross-trained this way with servers that are cross-trained this way, what happens? That's maybe less, that is something that maybe I need a simulation for, because maybe the answer changes based on the types of inputs or the demand, those sorts of things. So it's once things get to the point where an answer isn't even guessable without the sim, then that's really kind of a good sim thing. But I also don't want you to pick something that is infeasible, and so we totally understand that you've only we're working on this for a couple of weeks, so it's not supposed to be like a full semester term project, but at least still should be something that I always. When I ask other faculty to come in and review, a lot of times they'll ask, like, what other framework could you have used to solve this problem? And that usually is kind of their gentle question of saying, why did you do this in simulation? And so I don't want you to be asked those questions. And so I want you to sort of at least justify, like, oh yeah, so even if it's something that maybe if you were to drill down in the literature, people already know the answer to, it still isn't quite obvious, at least conceptually, so that you've sort of done it with a sim. So in the presentations, where you've got this limit of 13 minutes, so plan for 10 minutes of presentation and 3 minutes of questions and answers. And there's a little bit of time for switching, and that should give us plenty of time to get everybody done in their lab period. The groups, like I said, the evaluation, well, these external evaluators, so depending on availability, it might just be me and the TA, but hopefully we'll get a couple other people in here to give some other feedback, and then your attendance that day is a part of your grade, as you can see in the on the syllabus. So we're expecting everybody to hang around to watch everybody else in their lab section, just in your lab section. So, and the idea there is that there's every one of your projects is going to have its own peculiarity, and there's going to be some things that people have learned how to do on their own that we have not covered in class. And so my hope is that you'll actually learn something by seeing how other people solve the problem. It's also, we'll see a lot of similar systems, and so it's kind of interesting to see how other people solve the problem that you solve. And then questions end up being a good source for questions. Is that you guys, sort of your heads are already in it, and so you have usually some really nice questions, and I really encourage the questions from the floor. Then the project report we do the Saturday before finals week, and then the last deliverables we have to worry about that are non-report related. There's a couple of, there's this ICA, that's this review ICA. You can take as many times as you want. Then we'll have lecture M, which is the Tuesday before the final. And then the first final is on Thursday, and if you're happy with your score there, so hopefully, I'm going to try to turn those around, and if Scantron is behaving, then before the Tuesday of finals week, you'll hopefully have your scores in hand and decide if you'd like to take this one. If you just want to relax that last week of school, you can then you can skip this one and just come to the final. So it's no fault, whichever one you come to, the highest grade. I keep pointing to those, but I'm supposed to be pointing to these. But the highest one will take the score, exactly like the midterm. And it'll be midterm length, because in order, we have to shove the final into this period, so it's only going to be 75 minutes long. I'm still going to aim for it to be cumulative in spirit, but of course it's going to be biased towards new material that's kind of more statistical post-midterm. But expect to see at least one hand simulation problem on there, for example, to make sure everyone still remembers how to do that. So that's the basic outline. So if there are any questions, then let's hold off for a second since I was late, and we'll talk about Point Break. So the idea here that I've motivated is that we want to avoid point estimators. And so point estimators are a great way to summarize things to stakeholders maybe 2 or 3 degrees removed from the technical work, but they don't communicate any uncertainty, and that uncertainty is often the most important thing to communicate. So whenever possible, we're using our interval estimation. And so we're going to see if we read professional documents, if we read published literature, like this particular article that I picked out, then we see that whenever they give a point estimate here, like this is a 0.78 regression coefficient, they always give a confidence interval next to it. So they listed their lower and upper bounds right here, and then they even interpreted that because the lower and upper bounds do not include 1.0, and that is an important other hypothesis from the literature that they're testing. They reject 1.0, and because it includes 0.75, which is another debated one in the literature, then they say, and we find at least support for 0.75. We can't say for sure it's 0.75, but our confidence interval is this tight, and given that it's this tight, we still weren't able to reject it. So the confidence interval ends up being a much, much, much more useful tool than just saying it's 0.78. It really captures all of the fact that like if they only had 2 or 3 points here and they still got a 0.78, then this confidence interval will be so large that probably both hypotheses would be inside it and they wouldn't be able to say anything. So the fact that they've got a tight enough confidence interval that captures 0.75 but doesn't capture 1.0 ends up being really useful, and that's why that's all they really had to summarize right there. So the idea for us going into models, the simulation models, is that we're going to have these models, and every time you run them, you're going to get variability like this. And so you could say, I built a model of my simulation of Qdoba or Chipotle or whatever it is, or a call center, and I got this mean estimate out of one set of replications. But then the question is then going to be, well, how confident are you that this is a normal, that this is the mean performance? That this is the performance that if you were to run this again, you would actually get a similar performance next to that. And so you can list the variance, but the variance is hard to interpret. And so again, these confidence intervals become useful. So we would list a confidence interval for any one of these point estimates that comes out of your simulation. And the confidence interval will always have this half-width formula. So regardless if it's 1 sample or 2 sample, it'll always be the critical t-value times the standard error of whatever you're taking the confidence interval of. And so in the case of a 1 sample, so just an absolute measurement, an absolute performance estimate, there are the number of samples minus 1 degrees of freedom, which helps you calculate your t-statistic. The standard error of the mean is just the standard deviation divided by the square root of the number of samples, and then from that you can get your half-width centered on the estimate that came out of your mean, and now you can start testing hypotheses just by presenting your confidence interval. So you can just, if you, a lot of times you can just leave it like they did, and kind of in this paper back here, you can just show the confidence interval, and you don't have to belabor any points, because it'll be clear from the confidence interval that anything outside it you're rejecting, anything inside it you don't have much, you don't at least have support to reject. So useful tools, so in your homework you have to calculate a 90% confidence interval. People have asked, well, how should I do that? So either, of course, in the output analyzer you can tell it 90% confidence interval, and I know that's what some people have been doing, but if you just look at the half-width formula, then you can see that you can actually rescale one confidence interval to the other by looking up the two t-values. So if I look up the critical t-value for the 95% confidence interval, and I look up the critical t-value for the 90% confidence interval, if I divide the 95% half-width by the 95% critical t-value, and then rescale it up by the 90% t-value, then I will get the 90% confidence interval. So confidence intervals are just rescalings of the standard error of the mean based on these critical t-values. So if anybody gives you either a standard deviation or a standard error of the mean and the number of samples, then using the critical t-values, you can then choose whatever confidence interval you want. So in the output analyzer, you can choose this confidence level. But in ARENA, it's more difficult to choose the confidence level. It just will give you the 95. Well, you can rescale that to get the 90. So you don't have to, manually calculate it. If you've got one, you just look at the t-value and rescale. The other trick that you have to, we've seen a lot in the last labs and so on, is this half-width formula for if I give you a desired half-width, you can choose the number of replications. And to make things simpler, you approximate the t-statistic by a z-statistic. So you look up the z-table instead of the t-table. And if you've got your pilot standard deviation, you can pick the number of replications. And that will allow you to narrow your confidence interval to whatever you want it to be. So that was our one sample case. So then we moved on to two samples. So how do I compare these two models? So I've got maybe the as-is system, a proposed change. I've got a bunch of replications of both. How do I compare these two? And then that's when we came up with these two samples that are all summarized here. So they all have, again, this same format. Every half-width is just a standard error of the thing you're estimating, scaled by that critical t-value. So the only free parameters here are the degrees of freedom and the function for the standard error. So if I've designed my system to have paired differences, that gives it high statistical power, but I have to do a special experimental design ahead of time, then I have this formula to calculate my confidence interval. Instead, if I didn't design it that way, but I run a test like these to confirm that the two groups, both my Model 1 and my Model 2 groups, have the same variance, then I'm free to do a pooled variance t-test. And that has a little bit less power, but still pretty good power and fewer assumptions. And then I have another set of formulas for these degrees of freedom and the standard error. The only thing I know is that my outputs look normally distributed, but I can't say that their variances are equal, then I have a fallback. And that's this Welch's t-test, Welch's two-sample t-test, which has a very complicated formula for the standard, for the degrees of freedom, relatively simple formula for standard error of the mean. But if you have these formulas in your back pocket, then you can calculate these confidence intervals, and then you can just summarize your inference by just giving me the confidence interval. You can just say it was a Welch's two-sample t-test with a 95% confidence interval of this, and I can interpret that. You don't even, so in most academic papers, you'd also give the t-value and all of that sort of thing, but really, all I need to make an inference is just for you to give me the confidence interval. And so as examples, like here's just a random thing I pulled out of literature, and this is a particular piece of work where they did a paired difference t-test and it's a little hard to read, but they just report the mean difference. So again, mean difference, that's, I guess I didn't have to go back, that's just this right here. The mean difference between the two systems is, and then they gave a point estimate, and then they said the 95% confidence interval of the mean difference, and then they list the confidence interval. And then in this big block here, they show that all of these are quote, NS, not significant. And if you look, all of the confidence intervals they list include 0. And then down here, and it's a little hard to see with this blob here, but they have one where they list a confidence interval, a 95% confidence interval here, where it's all negative. And so here, because the 95% confidence interval does not include 0, then they conclude that these two groups are significantly different. So just by showing me the confidence interval, you summarize to me whether you have found significant difference or not. But now the confidence interval is in terms of a difference, and you're testing to 0, as opposed to an absolute value that you're testing to a particular hypothetical mean. So another example of that is when you pair your data. This is the common way, and we'll see this later today when we talk about common random numbers. So in sim, we do this a lot too. When you paired replicates. So in this case, this particular paper was actually written by another faculty member here at ASU. He studies ants. And so he had colonies from A through J, and he was testing them in 2 experimental conditions in the lab and watching how it affected a certain response that he could measure. And so each colony he tested under 2 conditions. And so because each colony might have their own peculiarities, he paired the outputs by colony. And he plotted one condition as circles and the other condition as crosses, and drew a line to show their differences. So this, in one plot, shows us the variance in the circles and the variance in the crosses, but shows that when we pair them together, then if we focus on the length of these lines, then the length of these lines is actually where the signal lies, and we don't have to worry about the fact that this colony is uniformly lower than, say, this colony up here. And we see that across all of these, there's only one colony where the circle and the X switch. And so he was able to conclude that because all of these differences were, all but one of them were in one direction, let's say they were all positive, then he was able to then use a pair difference t-test to show that these differences, that this condition, this one wall condition, is significantly different than the 2 wall condition. So it's a very nice way to summarize it. Again, we will see this way to summarize things again, where we are going to index things by the random number streams that we put into our sims. So it just shows that if we were to pair them up together, we might get confused because this colony might add a lot more variance to our estimates. But when we end up accounting for colony, controlling for colony, then that takes away the variance that we get from the colony, and instead allows us to just focus on the treatments. Now, if you don't have paired, then this is the way that we typically summarize our data. You have your treatments down here. So this is a study of the men that were less than 45 years of age and greater than 45 years of age, and they were studying a property called, yeah, question.
A quick question on the last plot, like why don't all the shifts start at 1 though? Like is it because it depends on like the data of the groups, or like why don't all the shifts start at 1?
Well, the response variable here just has, I don't mean by start at 1 because like this one goes almost down to 0, but this response variable, I'm not interpreting what this response variable is. You could say it's average wait time between customers or something like that. And so all we're saying is that in one treatment, the average wait time between customers across colonies was pretty much always shorter. And the other condition, so maybe this is with 1 server and this is with 2 servers. And so with one server, we always got an average wait time, except for in one unlucky case where it was always lower than the others. That's all they're sort of trying to say here. So I wouldn't pay too much attention to this, because this is just the units of the response variable. They're in centimeters right here. But more the idea that I can then plot my inputs as categorical variables And then above each categorical variable, my two outputs that were paired with it, and connect those. And that ends up being graphically shows that that even though I have significant variation, most of that variation comes from the population and not from the treatments. And the treatments pretty much uniformly have the effect that treatment X is higher than treatment open circle. So that's why we summarize it that way. And we'll see this again when we show this, but with these being input streams as opposed to colonies, but it's the same stats. All right, so if they're not paired, this is the preferred way to graphically summarize your data using either a box and whiskers or a bar plot. At this point, when you actually are doing a two-sample unpaired t-test, it's actually not super common to show the confidence interval itself because people have a hard time interpreting it. And if you just show them one confidence interval, then they oftentimes think that you must have paired the data together because it just conceptually, it's when you present it this way, it looks like you're saying, well, how did you generate these differences? What do you mean by a confidence interval here? So rather than going back through the kind of like t-test math, it's just easier to show the variance in one population and the variance in the other population, and then show some indication whether there's a significant difference or not. So it's a little less exciting than this, but it still communicates that not only do you see that there is a slight shift upwards here, but the p-value tells you that they are different here. But in order to interpret that, if you did happen to calculate this confidence interval, then this confidence interval for these two groups would not include 0. So that's just an alternative way to show two-sample t-tests. All right. So then the last thing that we covered last time was then the 3-model case or more. And we said that since we already know how to compare 2, then maybe what we should do with this is just compare every pair to each other and try to rank them. And so that's the most straightforward way to do ranking and selection. Just compare every single pair. So if I have k models, and so k choose 2 pairs, and if I do that, I can end up getting a lot of comparisons as my number of models k goes up. And the reason that's important is that in order to do statistically rigorously compare these and not fish for differences when they aren't there, each of my individual comparisons, my individual confidence intervals, has to have whatever my desired false positive rate is divided by the number of comparisons. And so if I don't do that, then I'm almost guaranteed to find a difference in the whole group of them together just because a few of the individual tests falsely found a difference. And so if I really want 5% at the family level, at the group level, I need much, much, much less than 5% at the pair level. And that's what this whole Bonferroni stuff is all about. And so the family level interpretation of confidence level is basically under the null that systems are equivalent, I falsely detect an ordering with alpha. And if I want that to be 5%, the individual pairwise comparisons have to be much, 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 much lower than 5%. And that's just the mathematics of how this thing works. If I flip a coin, if I want 10 coin flips to very rarely come up with a single head, then I need to make sure that a single coin flip almost never comes up with a single head. So if I don't want a false positive here, I really don't want a false positive at the individual level. And so that's very restrictive when you have lots of systems, and that's why we have the ANOVA. And so, and I added to it is I don't think you typically learn about the post hoc tests in 385, but if you have a bunch of data you can do an ANOVA on, and your ANOVA has come up significant, if you then want to rank them, then you go into a tool like the output analyzer, and I say I want to do a comparison now. I know they're significant. Do what's like a Tukey test or a Fisher's LSD. There's all of these post hoc tests, and that will add to your ANOVA, which would normally be these green boxes, things like these letters, which put them into ranked groups. And so these letters tell me that these two I can't tell apart, but I can tell the group of them together are very different from this group, which within the group I can't tell apart. And this intermediate one, which is labeled AB, I can't tell the difference between this one and this one and this one and this one. It's intermediate, and statistically speaking, I have no idea which group it's in. But I can definitely tell you that these two are different than these two, and vice versa. Yeah.
Quick question with the plot that's combining both A and B. Are you suggesting that there's a correlation between both groups?
It's not that there's because these were all independently done. So like these were 1, 2, 3, 4, 5 treatments. And so we're saying that, let's say I ran my system. This is like, this is one queuing configuration of the bank. This is another queuing configuration of the bank, and so on and so forth. I ran separate replicates, maybe with even different random number streams. And I got data that just happened to look this way. What this is saying isn't so much that there's a correlation between this group and the other groups. What it's saying is that performance-wise, I cannot honestly say that this group is better than this group. And I cannot honestly say that this group is better than this group. But statistically speaking, at least at a false positive rate of alpha, I can confidently say this group is better than this group. And that's what these post hoc AA, AB, BB are telling me. That's the way we read that. So that's like the sort of the gold standard of if you already have a bunch of data sets. So this is like a one-factor ANOVA. So I have this one factor with these multiple levels. And if I've got data for each level, and I want to say, how do these levels sort, and all the data is already there, I'm not going to run any more simulations, then the ANOVA is sort of the best way to do this. But we said that the downside of an ANOVA is that, let's say you did want to run more simulations. So you just want to run a little pilot study, and then from there decide what more simulations to run, and then maybe what more simulations to run. The ANOVA is not really built for that. And then also, I often don't really care about how the whole thing ranks. All I really want to know is about two groups, the best and everybody that's not the best. So it would be great if I could say, all right, I want the lowest average wait time. Well, maybe these are in the lowest average wait time. I can't tell the difference between the two, but I really don't care about any of these because I know that these are not the lowest average wait time. So don't even bother ranking them. So is there a way that I can get more statistical power by only focusing on two groups? And so we said that there's that the book gives you one method that if you're implementing this all yourself, you can do. But then I'm just sort of cutting to in the process analyzer when you ask it to do the equivalent of the ANOVA. So you give it multiple scenarios in the process analyzer, and then you go into a box and whiskers plot and you tick the box. It says select the best. That's effectively doing something like a post hoc test, but it's forcing it to only put things into two groups. The best, where you define that to be lowest or highest, and everybody else. And by doing that, it gets more statistical power, which means we can sort of trust it to have more sensitivity. And it still is going to have ambiguity. So in this case, if I went to lowest average wait time, either of these might be a good choice. There's one that is, if we had more data, we probably could sort one scenario lower than the other. But this is sort of telling us that, well, for the data you have, I know that there's probably not that much difference between these two scenarios, so it's probably not worth the extra effort to sort them out. Just pick one of these two, and you're not going to be that wrong. You're either going to be right, or you're going to be off by a little. And so, but definitely don't pick this one, because I've concluded, it's in a different color, that this group is significantly different than this group. And if I had multiple levels, even more scenarios, then basically you'd see a whole bunch of blue and then several red. And you basically pick any of the red, and that would be your good solution. So that would be one way to optimize across scenarios. So that's kind of going through. So, and then the last thing before I ask for questions is an OptQuest is your other option. And in OptQuest, it even does more for you. You basically say, now the only downside of OptQuest is, whereas here, I could put different models. I could have, this is a model from one DOE file, but there's one from a different DOE file, and so on. I could compare them all together. But then I have to select, so for this model, I want this many servers. For this model, I want this configuration. But if I just have one model, and I want to sort of sweep through a range of parameters within that one model, that's what OptQuest is great for. You load in the one model, you say, here's all of my 5 decision variables. Here's the ranges of my 5 decision variables. These decision variables are continuous. These are discrete. These are my constraints. I don't want this output variable, this response variable to ever get higher than this or lower than this. Given all of that, then choose the best subject to some other output variable. So choose the set of parameters that maybe reduces the power in a nuclear reactor simulation subject to this constraint that the temperature doesn't go above a particular level. And then it will then, once you hit go, you can watch it and it will run as many replications as it needs, and you can configure these things, and then it will then sweep through your decision variables as it needs, deciding to maybe spend more time studying some than others, and you just let the thing go, and in the end it comes out and it'll say, look, I found the best output, the minimal output was this one right here, and that corresponded to this set of decision variables. And if you want, then you can drill down into that and you can ask it, well, and how tight was my constraint being met? Like, oh, well, you were pushed right up against it. Well, maybe I want a little bit of margin, and so I can back up and say, maybe I'll choose this one. So it does all of that for you, and so it's sort of the ultimate tool in these SimOpt for automation, with the next step up being this process analyzer. All right, so that was just sort of sweeping through everything we've done so far. Any questions about this stuff? And that was sort of the end of absolute and relative performance estimation. We're starting a new unit. So any questions about this performance estimation stuff, comparing and optimizing across simulations? All right, so now we sort of move into design of experiments. So the idea here is that we now have sort of worked on what you would do with a simulation, and now for the last, this is effectively kind of the last major unit of the course. And it is basically how do we reduce the amount of computational time that we need to make a simulation just as useful as it was maybe with a higher computational budget. And so we're in the realm of so-called variance reduction techniques. We already assume you know how to build your simulation models. You already assume you know how to compare them. And now it's how do we better design our experiments so that we can use fewer replications and get the same statistical power. So the idea here comes from, well, if I am doing a performance estimate, let's say a mean like this, it's got this standard error. I look at the standard error and I know that I can increase my number of replications, and that will bring my confidence intervals down. But that's pretty costly to do. Is there some other way that I can kind of deal with the numerator? So somehow reduce the amount of variance that is in my estimator. And so this is, in experimental design, this is what we call control. So when you first learn about the scientific method in whatever, 4th grade or 3rd grade or whatever it is now, they talk about that you need a control for your experiments. They'll say I have a treatment group and a control group. And so you say, but what is control? So in statistics, control is the practice of accounting for sources of variance. So if I just run an experiment, like I say, wow, I ate a piece of taffy today, and boy, do I feel happy. So then I could say, well, taffy makes me happy. And you could say, well, but wait a second. You didn't control for the natural variation in your mood. Maybe you would have been happy today without the taffy. You needed a benchmark. You needed a control. And I needed a control for the natural variance in my mood. And so I somehow would need to rewind time and replay that day without me having the taffy and to see if I was similarly happy. And so that's accounting for the variance that I would normally get just by going through my day. And so control, whenever you hear that term, what it really means for is accounting for unexplained variance. So I've got this example that just came out, I think, a couple of days ago. So I reworked some of the slides to build this in. Hopefully it wasn't a mistake. And this paper came out where, I won't go into all the details here, but they basically were trying to study with faculty, early career faculty, in their first 3 years. They saw how many papers did they write with top authors. And you can define what you mean by top authors, but senior authors that are very well cited and very well known. And so they were interested in top co-authors in your first 3 years. And then it was a longitudinal study. So then they said, all right, and so we're going to study as a response variable the success in the 20th year of your career. And so, so that's what they wanted. They said, all right, what is the link between who you publish with in your first 3 years and how successful you are in your 20th? Now, immediately when you hear that, you say, wait, there's all sorts of confounding factors. There's all sorts of other things that could account for the variance that you see in the 20th year of your academic career. So you add in these so-called controls. And so what they said is, all right, we are also going to measure the effect of the institutional prestige of where this person was in their 20th year, the productivity of this person, the number of citations for this person. So basically they're saying we know that all of these things likely affect their success in their 20th year. But we really just want to focus on top co-authors. Our uncertainty, if we don't include these, is going to be much higher for the top co-authors. So maybe if we also model these, then we'll actually get less uncertainty for these ones right here. And so in one of their outputs that I've copied over here, what we see are confidence intervals on regression coefficients. And you can see that they're very small, and they're all to the right of 0, which means that all of these apparently have a significant positive effect. And so what they really cared about was just this little one down here. But in order to make that confidence interval small, so that, otherwise it probably would be so large it would include 0. But because they designed their experiment to also take into account that there could be an effect from these 3 other factors, they fit 3 other regression coefficients. So they effectively studied these 3 other things, even though they didn't really care about those, just so they could subtract away the variance that was caused by those, so that the remaining variance was small and the confidence interval here was made even smaller. So they controlled for variance from other factors in order to reduce the variance for this one. If I look down in their caption, then I see that this linear model right here had an R² value of 0.33, which if you remember our interpretation of R², that means that this linear model explains only 33% of the variance in this response variable. And that 33% of the variance is effectively divided up between these 4. It's probably mostly in this one. But then once you've accounted for the small amount of variance that, say, citations takes into play, that 33 now goes down to, say, 18. And then you account for it here, and now it goes down, 10. And then here, and now it goes down to 5. And now you're only explaining, whatever I have left. Let's say 4% of the variance left. But if I didn't include these, I might have to try to explain all the variance in the data. But by including these, I only have to explain a small fraction of the variance. And that's what we mean by variance reduction. We are controlling for sources of variance that we are able to tease out in our experimental design. And by doing that, reduce our confidence intervals and make it easier to make a clear inference. So what's an example of that? Well, we've already seen common random numbers, and we'll drill into that a little bit more. We'll also talk about control variates, which directly relates to what I just talked about. And then on Thursday, we're going to introduce these antithetic variates and importance sampling. And the thing that all 4 of these things do, and these are just the standard or the common ones that we first introduced as VRTs, and there are lots of different VRT techniques, is they all, in a different way, account for variance that otherwise would make our confidence intervals much larger than they need to be. So let's get a more clear example of what we mean by this. This is nearly the same slide I had the last lecture when I introduced common random numbers as an example of where we use the paired difference t-test. And the idea here was I'm going to take 2 simulations and I am going to run the same number of replications, and I will run the same random number seed into every replication number. So if replication 1 gets the same seed in both models, replication 2 gets the same seed in both models, and so on and so forth. So I've paired the 2 simulation models by the input number streams So I can compare within that. So for this input, how well did both models do? And it's compare their performance. And I can do that for multiple different input streams, just like I showed you with those ants. And the idea here is by introducing correlation between the two different groups, model A and model B, then the expression for the variance in their difference is reduced relative to what it would be if they were independent. And so I am reducing the variance, and that will end up making my confidence intervals smaller. And so this is the same thing that we sort of talked about for paired difference. We actually did this by hand in lab 2. So in lab 2, that was when you're simulating the muffin baking oven. Each one of you had a different schedule of muffins going into the oven. So you said, all right, I have this schedule that was given to me in the Excel spreadsheet. I'm going to run that schedule of muffins through both the greedy policy and the nearly full policy, and I will get an output in this group and then an output in this group. So each one of these dots represents the effort of one of you by hand working out that muffin baking simulation. Now the thing is, because these batches here are all the same as these batches here, we don't normally would portray them this way, because it hides the fact that some of these, like, I don't know, does this batch correspond to this batch, or does this batch correspond to this batch? And it would make a big difference. If I ran the same muffin schedule in, and the greedy policy came up this way, but nearly full came up this way, then it looks like, oh, maybe things were better in nearly full. But if I flip it around and actually it corresponded to this one, then maybe for this schedule, then actually nearly full is doing worse. So I'm not quite sure which one it is, and that's why I might actually depict them with these lines showing that for the schedule, like this schedule might be the, if the last digit of your ASU ID ended in 0, and I gave you the schedule for that, that might correspond to this pairing. And then someone else might correspond to this pairing. And now that I've paired them all up together, it looks much clearer that all of these lines are going in one direction. So that reduced the amount of variance. Before here, I didn't know how to explain the variance in these two. It kind of looks like this mean is greater than this mean, but there was a lot more overlap now. Now, when I put them this way, it looks uniformly, like for every single one of the 10 muffin schedules, every single one of them got better. Over here, I can't tell. Maybe these are the same performance as these. But here, it's clear that these ones down here are actually better versions of these, and these ones up here are actually better versions of these. And so by pairing them, I've reduced my uncertainty. And so going back to that visualization I showed you with that ant example, I can say, well, this is the pair for the schedule I gave you if your ASU ID ended in 0, if it ended in 1, if it ended in 2. By plotting them this way, then I can see that the greedy one, the open circles, are always beneath the nearly full one, the closed circles. And that tells me that there is always an improvement when I go from nearly full to greedy. So I have reduced the variance just by pairing these things together. There is variance that comes from the input that I have controlled for by making sure that I make fair comparisons. So if there's a really difficult input like this one, then I make sure that they both get it. If there's a really easy input like this one, then I make sure they both get it. And I don't compare an easy input with a difficult input. And so I can now take all of these differences and plot them just as differences in a one sample configuration here, and I can see that all of the differences are less than 0. And if I did a paired difference t-test, I would find significance. Or at this point, I could do a one sample t-test just on the differences. It's identical, and I would find significance. And so that is an example of one way we reduce variance by making the inputs identical. Your book has a nearly identical depiction of this. And so in your book, they simulated an MM1 queue and an MM2 queuing node. So if I look at both of those, MM1 and MM2, they both got the same arrival rates. They both got the same service time distributions. What do we expect to happen? If I go from an MM1, just as a reminder, that's with one server, and an MM2, that's with 2 servers. The only thing that changes is the number of servers. And they're measuring, let's say they're measuring the average wait time in a queue. So take 30 seconds and just wake up and just try to, and we can make this an attendance question. And so the question here is, what do you expect just by queuing theory to happen to the average wait time when you add a server to an MM1 queue to make it an MM2 queue? What should we see? So, and then because it's an attendance question, I'll go back to find a QR code here. There we go. So MM1 to MM2, what happens to the average wait time when you go from an MM1 queue to an MM2 queue? What should we expect when you add a server? All right, so let's bring it back. So how many people would say that if I'm measuring the average wait time, and I've gone, so which one, in which system, so I'm going to put my hand across one of these, and raise your hand for your vote as to saying which one has the higher average wait time. Does an MM1 have the higher average wait time? Does an MM2 have the higher average wait time? Looks like everybody said that MM1 has a higher average wait time. Why? Anybody? What's the rationale?
Because there's more people or machines or whatever to speed up the process.
That's right. So we would expect, this is an example of something that you shouldn't do in sim, because it just makes sense. As you add a server, then there's going to be more work done reducing the queue length. And so the average wait time should go down because you're getting more work done. So we didn't change the arrival rate. We didn't change how fast each individual did anything, but we just doubled the number of individuals. And so we would expect a decrease in the average wait time. Now, so when they did this simulation, just to prove a principle, then they've got in their first plot, this is what things for the unpaired. And so they're showing pairings here just to make kind of an apples-to-apples comparison of the two plots. But basically they have that the open circles are the 2 server queues and the closed circles are the 1 server queues. And it may be hard to see, but I hope you can see at least sometimes the open circles are above the closed circles and sometimes the closed circles are above the open circles. So basically they're saying that we've paired the replications together, but for this particular replication, we didn't run the same inputs through. So even though they were both described by an exponential with the same rate, the actual customers that went through the MM1 and MM2 queues might have been different. And so the differences I see here might just be that this system got a really lucky set of arrivals and this system got a really unlucky set of arrivals. Now, to make it a fair comparison, I run the same customer streams into both. And then I plot it and I get this output. And now it is very clear that the closed circles are always beneath the dark circles. In other words, the average wait time is always less than the average wait time for the MM1 because the MM2 has another server that's helping out with that queue. So there's not a very large difference. But that shows that even though the effect is super small, by using this common random numbers technique, I'm able to detect the effect. Look at the huge variance that I have here. This is gigantic. The effect that I'm looking at is this big. If I go back here, that is fractions of a standard deviation of variance. And by pairing the inputs together, I effectively subtract out all of the variance that's just due to the bad luck of drawing a certain input stream. And now I'm able to amplify even the tiniest of differences between those two systems. So that's like the power of this method. So if you want to use this method in ARENA, if you drill back into your minds to when we talked about random number generation, I said there's a seeds block inside the elements block, which you can use even if you're not using any other elements from the elements blocks. If you drill into that, you can then add your own stream. And then in that stream, you can name it, or you can use one of the standard numbers, like 10 is the default one. You can leave the seed value blank. It doesn't matter here, but under initialize option, there is a common. And if I select that common, then what that's going to do is every time you run a replication, the next replication will start with a seed that's 100,000 more than the seed before it. So it basically says, regardless of what happens during one replication, my next seed is going to have a predictable value. So if I run 10 replications, then the first seed will start with whatever the first seed started with, and then all the other seeds I'll know. And so if I do this for multiple models, so I open ARENA, close ARENA, open ARENA, close ARENA, but they're all initialized this way, then I know that they're all going to have the same random number seeds going into both, and I'll be able to compare them using paired t-tests. And so inside ARENA, once I've done that, if I've got like an expo, I can add after the last parameter for each of my random variables the name of whatever stream I added, and it will make sure to use those common random numbers. And if you initialize seed 10 to be a common random number stream, then even without adding that, everything will be running on the common random number stream. And that allows you to pair your outputs in Output Analyzer, in Excel, however you like, because you're guaranteed that every replication across models starts with the same seed. And so that's just showing how to do that, and then the pair difference t-test. So the downside of CRN is it doesn't always work. A really good set of arrivals for my system might be a bad set of arrivals for yours. It only works if uniformly across both of our systems, there's like one bad way that things could happen. So if it's really bad that I get a burst of arrivals at the beginning of the hour, and that's bad across both systems, then CRN will work well. But if you've built a system that's optimized to handle bursty traffic, so it might be really bad at other types of traffic, putting a burst of traffic into two systems, one that's optimized for bursty and one that's not, is not going to provide you any variance reduction. So this is another one of those examples that before you go and do a big CRN study, you should do a small study where you actually test whether your variance is reduced by using this method. Now the last short method that I want to bring up in the last couple minutes here goes back to my motivation for this whole VRT, this idea of controlling for sources of variance. I've already shown that CRN controls for the variance you get from the random number streams, but we can also be a little more methodical. What if we have an output Y of our simulation, and there is some other input X that we know is going to have some correlation to our output? This is not the factor that we're interested in studying, but we know it is going to have an effect. Well, what we can do is we can measure the correlation between this input and this output and subtract it off so that whatever's left over is the variance that we'll actually use to do our real estimate. And that's exactly like what they did in this paper that I showed in the beginning, where they were only interested in the effect between this predictor and the response variable, but they knew that these predictors would also have an effect, and so they had to model those and subtract out their effect, and that made this effect much more clear. And so what we can do is we can basically say that if I have an input coming into my sim, that I call X, I can take my output Y and build a new output Z, which is going to just be the difference between the input and its mean times some value that I'll have to solve for in a second. And so all I'm doing is I'm taking my normal output and I'm adding some fraction of the difference from this input. And by doing that, there's no bias in this estimator, because if I take the expected value of this, I end up coming out and saying it has the same expected value of Y. So I haven't introduced any bias this way, but what I can do is account for variance introduced by this input. So if I solve for the variance expression here, if I take the partial derivative with respect to C and solve for C, I get this function down here, which tells me that if I measure the covariance between the input that I have, X, and the output, Y, and I divide it by the variance in the input, that tells me the optimal way to scale this so that my predictor here will have minimal variance, and I'll be able to use that for my estimate of Y instead of the Y data alone. So this is me controlling for the variance introduced by X. And so yeah, I don't have an example of that. So if I plug in that into this expression here, then I end up finding that the variance for Z is going to be the variance of Y minus, and this is always positive. So this is something you can apply uniformly without pilot data. If there's no covariance between the input and the output, then this thing will be 0 and the variances will be identical. But if there is covariance, then this approach subtracts out the variance due to the input so that whatever's left over is going to be a lot smaller and my confidence intervals will be a lot smaller. So I think I do, somehow I deleted the example. So I do have an example of this that I'll put back into the slides that I implemented in MATLAB. But the whole idea here just comes back to this guy here, where you can have an input coming into your sim that you know has variability. So that's like a random number stream, for example. You can take the mean of that input. For every replication, you can look at how the input varies from that mean, and then use that to subtract off variance from the actual output that you want to look at. And that's another common way of reducing variance in your outputs. So those are the VRTs that we were talking about today, common random numbers and CVs. The last topic we'll talk on Thursday are AVs and importance sampling. And then after that, it's basically just an overview with some more sophisticated examples from SIM that we'll cover on Tuesday of next week before the final exam review on Tuesday the week after that. So happy to take questions, but let's give one more quick attendance response. And that attendance response is, what is the statistical test you use when you're using common random numbers? To compare two models that using the common random numbers technique, which statistical test should you use? Just comparing two means, but which means test should you use when you're using common random numbers?
Some of the attributes and just keep one of them and predict based on that.
You mean for control variates?
Yes, control.
It's not so much removing an attribute, it's kind of like if you, it's more of if you've got, like if you've got data sources that are coming in.